Good afternoon, everyone. Myself, PUNNAM. I am working as an assistant professor in EEE department, MLRITM. Today, I am going to explain the concept of block diagram reduction technique. The block diagram reduction technique, the block diagram algebra, the outer line of presentation of the block diagram is block diagram reduction algebra, block diagram representation of a system and its component, block diagram reduction rules with one example. A block diagram is basically a modeling of any system or a complex system. It consists of multiple blocks connected together to represent a system to explain how it's functioning. And the definition of a transfer function, the transfer function is defined as the Laplace transform of output to the Laplace transform of input with all initial conditions set to be 0. So block diagram have mainly 4 components. First one is blocks. To represent the components are a subsystem, that is G of S is a one block. And the next one is arrows. To represent the direction of the signal flow or a flow of a signal can be represented by a arrow indication mark. Next, summing point. To represent the summation of a 2 or more signals, this kind of representation has been done. So this is a summing point where the U1 of S and U2 of S, 2 signals are entering into a summing point. The output of it is U1 of S minus U2 of S. One is plus and another is minus. And the takeoff point. To represent a branching of a signal. So this is a takeoff point which can be represented as with a dot or a node. Typical block diagram forms. First one is cascade or series of connection. The components or a subsystem of a systems are connected in a series, each having its own transfer function. The overall transfer function is a product of individual transfer functions. For example, there are 3 block diagrams are connected in series or connected in cascade form: G1 of S, G2 of S and G3 of S. Okay, so overall transfer function output by input Y of S by X of S is equal to the product of 3 blocks G1 of S, G2 of S and G3 of S. Next, typical block diagram representation is parallel combination or parallel form. The components or a subsystems of a systems are connected in a parallel. The overall transfer function is a summing individual transfer function. Summing individual transfer function. So G1 of S, G2 of S and G3 of S are entering into a summing point with a certain signals. That is, here the output is X of S into G1 of S. Here X of S into G2 of S. Here the signal is X into X of S into G2 of S. So these 3 signals are entering into a summing point. The output is G of S. Overall transfer function is Y of S by X of S. Output by input is equal to this by adding all 3 blocks. Block gains G1 of S plus G2 of S plus G3 of S. Okay. Next, feedback form. One component is present in the feedback loop of another component. So here the feedback signal is a H of S. H of S is representation of the feedback. So now X of S is a signal which is entering into a summing point, and it is passing through a gain of a G of S, and the Y of S is the output. This is input and this is output. This output is again connected through a feedback network to the input, and the difference between this is called as error signal. So this kind of system is called as a negative feedback control system. So gain of this particular transfer function is output by input X of Y of S by x of s is equal to g of s by 1 plus g of s into h of s. So this is, if it here it is a positive, then the system is a negative feedback system. If it is a positive feedback system, then here it will come minus. So 1 minus g of s into h of s. Next, block diagram reduction. Block diagram reduction refer to simplification of a block diagram of a complex system through a certain rearrangements. The simplification enables any calculation of the overall transfer function of a system. The simplification is done using a certain rules called as rules of block diagram algebra. Rules of block diagram algebra. So first rule is combining blocks in a cascade. As we have discussed earlier, I am combining two certain blocks which is having a gain of z1 and z2. These two blocks are unconnected in a cascade mode. So overall our equivalent block is g1 into g2. And combining the blocks in parallel combination. This is the second rule. So if I connect a two blocks in parallel, are entering into a signal summing point. Okay, so here as I told you earlier, here signal is u into g1 and here signal is u into g2. So plus u g1 minus u g2. So if I take u as common, g1 minus g2. If it is plus here, then plus will come here. So that's it. Next, the total or equivalent block diagram is G1 plus or minus G2. That depends upon the symbol here. Next rule, eliminating the feedback loop. So eliminating the feedback loop, this is a positive feedback system or negative feedback system. If here here it is a positive, then it is a positive feedback system. If it is a negative, then it is a negative feedback system. For positive feedback system, transfer function gain is equal to output by input, which is equal to g by 1 plus gh. If it is a negative, 1 plus gh. If it is a positive, 1 minus gh. That's it. Next, interchanging the summing points. Suppose there are two summing points are connected in series, are connected back to back. Then it can be interchanged without disturbing the signal flow. So suppose here the signal entering is A plus, and here it is entering a B signal. So the output obviously A plus B. So this signal is again entering into this summing point. The output of this signal is A plus B or A minus B plus or minus C. So output has to come this. Even you interchange these two signals. So see here I am interchanging these block diagrams or these summing points. Equivalent summing point is A and C. These two signals are entering here. So output is A plus or A minus C. A plus or minus C. And this A plus or minus C is again entering into this summing point, and output of it is A plus or minus C plus or minus B. So these two are equal. So we can interchange the summing points. Next, moving a summing point after the blocks. So here it is a summing point. I am moving this summing point after the block here. So before shifting this, I have to calculate the signal or equivalent signal for incoming and outgoing of this summing point. So U1 is incoming here and U2 is incoming here. So the output of this summing point is U1 plus or minus U2, okay, which is passing through the G. So this signal is passing through the G. So output would be G into U plus or minus U2, U1 plus or minus U2, G into U1 plus or minus U2. Output must be same in the both the case, even you interchange the summing blocks or moving a summing box after the point, after the block. So see, so this is the equivalent for this. Now here it is the U1 is signal is entering into the G, and output of a G is U1 into G. And this is again entering into the summing point, which is U1 G plus again this signal U2 is here, it is U2 into G. So total output is U1G plus or minus U2G, and this must be equal. Both are equal. So I can interchange it. So this is the concept of block diagram technique. Next rule. Moving a summing point before the block. Now I am moving this summing point before the block. Same rule. So this mathematical expression incoming outgoing should not be disturbed. Even you interchange the summing point before the block. So here it is incoming or input signal is U1, and here is also U1, and here it is U1G plus or minus U2, and here also U1G plus or minus U2. So I can interchange the summing point before the blocks by adding one extra gain, that is 1 by G1, 1 by G. So next technique is moving the takeoff point after the block. So this is U1 signal going or entering into a G1 block, and the output is U1G. And if I take a point or a node from this point, the takeoff point is the signal over here is also U1. This signal only appear. So if I move this takeoff point before the block, even the block output must be U1. So what I have to do? I have to divide 1 by G with U1. So see, here it is U1 signal is entering into G block, and the output of it is U1G. And this U1G is input for this U1G, and output of it is 1 by G into U1G, because these two are in cascade. So GG gets cancelled, the output remains same. It means even you interchange or if even you move the takeoff point before the block, the output remains same. Next technique or next rule is moving a takeoff point before the block. So now this takeoff point I have to move before the block. So here the takeoff point magnitude or a transfer function is U1 into G. Even I shift to the left or before the block, it should not be changed. So for that, what I have to do? If I want to shift this takeoff point before the block, I have to multiply with a certain block that is called as G. When you shift the takeoff point before the block, you have to multiply signal with G. If you want to shift the takeoff point after the block, then you have to divide with 1 by G. That's it. Next. So let us solve one problem which is important for academic examination. So determine the transfer function of the following blocks. So first of all, I have to observe the question. What are the different rules I can able to apply? What are the different rules can I apply? So see here. So these two signals are G1, G4 and G3 are entering into this box or summing point. But this is a feedback path. So I have to replace this reduction. I have to apply the summing point reduction technique for this, and then I have to apply for the feedback reduction for this. And this is also one feedback network. And after that, this block, G2 block and this overall block are connected in cascade. So I have to apply three principles, three rules I have to apply here. Actually, this arrow direction is like this. So all the three signals are entering into a summing point. Okay. So the resultant reduction of G2, G4, G3 and G5 is G3 plus G4 plus G5. So in the next figure, I have to replace these yellow color blocks with a G1 plus G3 plus G4 plus G5. So this is the block. And these two are connected again into a cascade. So I have to multiply it. G2 into G3 plus G4 plus G5. See here, G2 into G3 plus G4 plus G5. So next, Next, third rule I can apply that elimination of feedback. As I told you earlier, this is a feedback network. Negative feedback, to be specific, it is a negative feedback. So signal is entering like this, and the this is the feedback path. So the total after elimination of this, we will get that G1 by 1 plus G1 into H1 in place of this yellow color black box. So see G1 by 1 plus G1 into H1. So again these two signals or two blocks are connected in a parallel, in a cascade. So I have to multiply this 2. So G1 1 plus G1 H1 into G2 into G3 plus G4 plus G5. Okay. So the overall transfer function is G1 into G2 into G3 plus G4 plus G5 by 1 plus G1 H1. So this is the total transfer function. Again, we can observe that one feedback loop is forming. H2 is the feedback for this. So this overall transfer function is again we have to reduct. So see, this is my overall transfer function and this is the feedback. So now G1 G2 into G3 plus G4 plus G5 by 1 plus G1 H1. This total is G plus 1 plus GH, no? So G1, G2, G3 plus G4 plus G5 by 1 plus G1 H1 into the feedback path, that is H2. So after simplification, we will get that G1 G2 into G3 plus G4 plus G5 by 1 plus G1 H1 plus G1 G2 H2 into G3 plus G4 plus G5. This is the overall gain or overall transfer function of a given problem. So whenever the problem is given, first we have to observe the problem. So after observation, what are the rules we can able to perform? So one by one we have to perform it. So next problem is determine the transfer function of the following block diagram. So if I observe this block diagram, I can find that here it is a feedback loop. I am able to see this is a feedback loop, and these blocks I can interchange these two blocks. Then again it will become a feedback path, and after that this total will become again a negative feedback path. So let us solve this problem by applying step by step different rules. So first of all, first rule I am applying is eliminating the feedback of the loop. So see G2 and H2. G2 is the forward path gain and H2 is the feedback path gain. So this I am eliminating this. So feedback, no. So after elimination of this, so I will get G2 1 plus G2 into H2. Here it will get G2 1 plus G2 into H2. Okay, G2 by 1 plus G2 into H2. Now you observe it, you will get rule number 1, 2, 3 cannot be used directly. So use the rule number 4 and interchange the adding, as I told you earlier, interchange the summing point. So this is 1 and this is 2. First summing point and second summing point. Now I want to interchange it. So after interchanging, I will get a signal like this. So again, this is a feedback, forming a feedback path, feedback loop. So this will be G1 1 plus G1 into H1. So in place of these yellow color blocks, I can represent it with 1 plus G1 into H1. So again, see, these two blocks are connected in cascade or series. So the overall transfer function is 1 plus G1 into G2 by 1 plus G1 H1 into 1 plus G2 H2. Again, see this total block diagram, and this is a feedback path. This is a feedback path with a unity feedback system. So see, So this is the feedback path, this is the forward path gain, and this is the unity feedback. Okay, so now I can perform a elimination of feedback rule here. So G and this is H, where H is equal to 1, feedback is 1. So G by 1 plus GH, actually it is H, where H is equal to 1, so no need to write H again. So G by 1 plus G. So what is actually G? G means this total product, G1 G2 by 1 plus this total. Now G1 G2 by 1 plus G1 H1 plus G2 H2 plus G1 G2 H1 H2 by 1 plus G1 G2 by 1 plus G1 H1 plus G2 H2 plus G1 G2 into H1 H2. After simplification, you will get finally G1 G2 by 1 plus G1 H1 plus G2 H2 plus G1 G2 H1 H2 plus G1 G2. So this is my overall transfer function. So let us solve another problem. So find the transfer function for the given block diagram. Okay. So this will be done in the next class. Thank you very much.